Okay, so I'm going to do another quick run through of the 6.2 notes just because the same audio issue that happened with 6.3 happened with this set of notes. Not sure exactly why, but I'm going to try to keep this short so that I don't have to take a ton of time to do it again. We did a little activity at the very beginning of class. We had Harvey shoot 10 trash basketballs into the trash can. And we asked him how many did he think he would make. He said 8 of the 10. So that claim 1, that initial claim proportion is P is equal to 0.80. I then asked the class what they thought Harvey would do, and they said they thought it would be less than that. So P is less than 0.8. And so both of those turn into our hypotheses. Harvey's original claim is P is equal to 0.8, so that is our null hypothesis. What the class believes will actually happen is our alternative. So what we did was we went out and we collected sample data. So we had Harvey shoot the 10 baskets. And after he shot his 10 baskets, he made 3 of the 10. So that was our sample proportion. So that was P hat, and we got 0.30. So we answered a couple questions about what we think based on our collected data was happening and what was actually happening. So the first question was it exactly the claimed proportion? No, it didn't end up being 0.8. We got 0.3. And do we expect it to be? And in most cases, not really. Just because you think the proportion of getting heads is 0.5 doesn't necessarily mean you're always going to get 5 out of 10 heads. So you're not always expected to get the population proportion. Can they have gotten the sample proportion and their claim still be correct? Yes, absolutely. It could have just been an off day, or it could just have happened by random chance. Even when we have a coin, just going back to that example, where we know it's a 50% chance of heads, there's still a chance you could flip that coin and get all tails. That is a complete possibility from just random sampling. So how can we decide if the difference is chance variation or if the original claim is incorrect? We basically go in and we look at how large of a difference do we have? Is it large enough for me to say, okay, the sample that I got is super rare and I wouldn't expect it to happen, and it did. So that kind of makes me suspicious of what you are saying originally. So we kind of started going into the nature of what a hypothesis test is. There are 2 kind of categories you can fall into. It can be a one-sided hypothesis test, or it can be a two-sided hypothesis test. So the one-sided hypothesis test is going to kind of go in a specific direction. So it's going to be something more or less. So those are going to be kind of the keywords you're looking for when you are doing a one-sided test. And it's always going to be against a claimed proportion, and that's going to be given in the question. So that's what we note as P naught. And you're always going to use the same value. So notice on the right-hand side where I have the HO and the HA written, I have P is equal to P naught, P is less than P naught, P is equal to P naught, P is greater than P naught. I do not change that value at all. It's going to be the same number written twice, once in the null, once in the alternative. Now we go to our two-sided hypothesis test. So this is going to be a case where in the question itself, they use the language of different or not equal to or not the same. They basically don't indicate a specific direction that they are looking for. So they're not going to say, we think that it's higher or lower. They just want to know, is it different than what they are claiming? So the reason why this kind of boils down to being a two-sided test is because it could be less or it could be greater. And so we kind of have to take both possibilities into consideration, which is why we have the not equal to sign. So One thing about the nature of this test and the way that the AP questions are going to be written, you're going to know your sample ahead of time. So you're going to kind of see if your sample is higher or lower than the claimed proportion. You cannot go back and change the alternative. Go with the alternative you would normally write based on what they are saying. Don't write an alternative based on the sample proportion. So if they say the word difference, use not equal to. Even if you look at the sample and you notice that it's higher, still use not equal to. Don't switch it up. Don't go to greater than. A significance test asks the question, how likely is it to get a result like this just by chance when the null hypothesis is true? So everything we do within a significance test, I like to say it's kind of petty because you're doing it with this understanding that, okay, I'm going to believe what you say. I'm going to do all of this math with whatever claim you tell me. I'm going to calculate a probability and I'm going to get this value. And basically what we want it to do is we want it to prove them wrong. We want to say, we did everything that you told us. We followed every avenue, every probability, proportion that you gave me. And still the statistics, the data are saying that you're wrong. So it's always under the assumption the null is true. And it's technically a conditional probability because we are finding the probability of something happening given that the null and the claim is originally true. So if we find the conditional probability and it's small, so if we go in and we calculate this probability value, that is good evidence against the null. Now, the probability of the event occurring given the original claim is true is called a p-value. So a lot of what you're going to see is us comparing a p-value to a specific significance level, which is going to be one of our terms in just a second, and seeing based on this relationship, should I agree with what they are claiming? So should I take on their claim proportion, or do I have enough evidence to go against what they are saying? So now let's go in and let's kind of look at what a p-value is. So p-value, that is a probability computed assuming the null is true, that the statistic p hat would take a value as extreme or more extreme. So one thing to kind of take into consideration is we're not necessarily interested in this one particular value. So if I'm saying it's less than 0.5, I don't need to just look at 0.49. I need to look at everything that is less than 0.5. And so we always do it in the more extreme direction. So we're going in and we're shading everything above or shading everything below or everything outside of these specific claimed values. And we're kind of looking at the difference between those observed p hats and our claimed p naught. So if the probability is large enough, so say for instance, I do all of this, I calculate it, I get a probability of 0.4. That means if the null were true, there's a 40% chance of me getting this particular sample, which is pretty high. Like, yeah, that could probably happen. So I can't disagree with what they're saying. But if I go on and I do all of these calculations and I get something like there's a 1% chance of me getting this sample and I collected it, that's when I have enough evidence against the claim. So I can go in and say their claim is incorrect. So how low is a low enough probability? That's where the significance level comes in. So our significance level is referred to as alpha. It's a little kind of fish-looking symbol, and we've kind of been dealing with alphas already in this class without it being kind of a formal alpha significance level p-value type question. We have talked about in our regular probability calculations, if something was less than 5%, less than 0.05, we consider it to be unusual, we consider it to be surprising, and that tends to be the problem. And that's exactly what we do here. If our p-value is less than alpha, we consider it to be statistically significant, and we reject the null. So there is convincing evidence in favor of the alternative. I like to say, and you guys don't get to have it as funny as we say it in class, if the p-value is low, you reject the hoe. And that is the easiest way to remember what decision you should make when you are trying to complete a significance test. So if the p-value is less than alpha, you reject. If the p-value is greater than alpha, it is not statistically significant. We fail to reject the null. There is not convincing evidence. We basically have to go with what they are saying the claim is. We believe them. We think it is true. The most common significance levels that you will see are 0.0, 0.05, and 0.1. If you don't get a claim that is given to you, we typically just assume it's going to be 0.05. And that's kind of what we run with if we don't have a value given to us, kind of what we used originally in our very early probability questions. The next page just kind of goes into the mechanics of the test. We have the one-sided tests. We have the two-sided tests. Again, always shading in the more extreme direction. The shading itself represents the p-value. The one thing about the two-sided test is it's got symmetry. So you really only have to find one of the areas and just multiply it by 2. The steps that we did for the actual significance test are kind of the same 4 that we've been doing. We're going to communicate the parameter. The only thing we're going to do is add in the identify hypotheses and the significance level. We are going to check conditions. One change here from the confidence interval, which is written off to the side, is that we are going to use the claim from the question. Remember, we're being petty. We're doing all of this with the whole, I'm going to believe you, I'm going to go with what you say, and I'm still going to prove you wrong kind of mindset. So we take on their claim, we use it to check large counts, and that's how we go through our 3 conditions. We calculate. One big thing, because we will talk calculator in just a second, if you want to get credit for calculator work, you do have to name the tests. So we typically say one sample, z-test for proportions. I added in the note of population, not because you have to write it, but because there are questions that will ask you multiple choice wise to decide between 2 phrases that look exactly the same. And one will say for sample proportions and one will say for population proportions. You are always making inference about a population. You are never, ever, ever making inference about a sample. If you see sample in the name of a test, you can automatically eliminate it. It is not the right answer. You are always trying to find out information about a population. You already know sample data. You don't have to figure that out. The calculation for the z-score. Z-score and test statistic mean exactly the same thing. I know in MATLAB, it's probably going to ask you to state the test statistic because that will eventually kind of be the common term when we kind of switch to a different test distribution. But Z-score in this case, that's all you're trying to identify. That's value minus mean over standard deviation. What you'll find when I actually go in and work this FRQ in just a second, I don't calculate mean and standard deviation in the conditions like we used to. I'm just going to calculate them in the test statistic itself. The next section just kind of talks about calculating p-values. This is going to normal CDF, identifying your lower and your upper. The one note, again, that I made for the difference one is that you only have to find one. So I did negative infinity to negative z, and I just multiplied it by 2. Now, in real practice, you would write out normal CDF. You would write out lower, upper, mean, standard deviation. But we were just trying to get through this kind of quickly now that we've kind of talked about all of it so far so that we can actually try it in a problem. So I just kind of abbreviated this with the image that matches the direction for less than, greater than, and so on. The conclusion is always going to be the same. You are going to plug in your p-value. You're going to plug in your significance level and the context to the question. The stuff that I have shaded together, so less, reject, and is, will always go together. And greater fail to reject is not, will always go together, because if it's a p-value is less than alpha, you will reject. If it's a p-value is greater than alpha, you will fail to reject. So I suggested that they highlight them in the same colors so that you know those decisions will always go together. So then we kind of got to actually doing an FRQ. For example 1, a National Health Survey reports that 80% of U.S. teens eat breakfast every day. That is my claim. That is my P0. And Jordan believes that it is less than that at her school. And so she takes a simple random sample of 60 students at the 5% significance level and finds that 41 say yes. So anytime you see, is there convincing evidence, that is going to be an indicator that you're doing a significance test. Communicate is going in and writing out our parameters. So our P equals proportion of students at Jordan's school who eat breakfast every school day. For the null and the alternative, you want to include your parameter. So notice I have P equals 0.8 and P is less than 0.8. A lot of the time I will see what is off to the right-hand side. HO equals 0.80, HA, that should be a less than 0.80. But if you write that, you are not going to get credit. If you do not include the parameter, the P, you will not get credit for your null and your alternative. They do not give it on the AP exam. I went ahead and identified my significance level. It's 0.05. That's what I'm going to use to compare at the very, very end when I start making my conclusion. So in this case, I went ahead and checked my 3 conditions. This should be something that you are very, 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 very familiar with. I checked random, I checked normal, I checked independent. The only thing that I'm really going to point out here is that for the normal condition, I did use 0.80, which is the claimed proportion. I did not use 41. If I were doing a confidence interval, I would use 41 because that is the claimed, like the sample proportion. That would usually be the only piece of data that you have. But in our case, again, we're living in their world. We're focused on their claim. So everything that they tell us is what we're basing all of our calculations on. So we're going with 0.80. Everything ends up passing. Again, I did not calculate the mean and standard deviation here. I'm going to calculate it within the calculate section. So all of these conditions should look familiar. They should look the same. They are no different than what we did in Unit 5 for sampling distributions of proportions. Now, for the calculate part, I went ahead, I labeled the test, one sample z-test for proportions. Now, I calculated the z-score, so I plugged in my p-hat. That was the 41/60 value, and that got me 0.6833. I plugged in my p-naught, which again is the claim from the question. That's 0.80. And then I put it over the standard deviation. Now, again, I did all of the calculating within the calculate section. I know back when we were doing this in the sampling distribution problems, we did it within the conditions and we just plugged in our values. You can still do that. I'm kind of moving you towards more of a place where you're going to answer this using the calculator and not necessarily calculating it by hand every single time, just again, for the sake of time. So that is why I'm kind of shifting things around so that you're not necessarily putting in and wasting time on work that you don't necessarily need to get full credit on an FRQ. But just to show you how it works, we get a z-score. It's negative 2.2599. I take that z-score, and because I think it's less than 0.80 based on my alternative, I'm shading below the z-score. So my lower is negative infinity, my upper is negative 2.2599, mean of 0, standard deviation of 1, again, because it's a z-score, a test statistic. And then I get my p-value of 0.0119. So I have everything I need to be able to answer and conclude this test. So the p-value is less than alpha. It's low. If the p-value is low, you reject the hoe. So since our p-value of 0.0119 is less than alpha, We reject the null. There is convincing evidence that the true, and this is where you come in and kind of fill in the alternative hypothesis. True proportion of students at Jordan School who eat breakfast is less than 0.80. So you want to give context. And the reason why you want to give context is everything that we kind of did in this calculate section here can be replaced with the calculator. The highlighted parts are really the only thing you have to have written down on your paper. And all of that, except for the name, comes from the calculator. So I'm going to go ahead and open mine up really quickly. Where you're going to want to go is you're going to want to go to Stat, over to Tests, and we want to go to option number 5, a one-prop z-test. And it's going to ask you a couple of different things. It's going to ask you what's the null proportion. In our case, that's 0.80. It's going to ask you for the number of success, which was 41, and the sample size, which was 60. And then it's going to ask you what your alternative hypothesis is. Typically, I say go to where you wrote down your alternative, look at the direction your inequality is facing, and pick the one that looks exactly the same. You would be surprised how many people just mess up by picking the wrong inequality in this part. And then all you do is hit calculate. And what you should get is you should get some numbers that look very similar to what we got on our paper, negative 2.259. It may be slightly off just because of the rounding of our values, but you should not get something that's going to completely differ and change your conclusion. So I got 0.0119 as my p-value, which is what I got when I calculated it by hand. So I can literally take my p-value, my p-hat, my z-score from the calculator, and that's all I have to write down. You don't have to do any of this work. Now, it's good to know it, again, because there are multiple choice questions that ask you to plug these values into equations, but you really don't have to do a ton of math, and that is one of the reasons why they make you interpret in context, because they know they can get all of this information from their calculator. They really don't have to do any big number crunching. What we need to know is that you can tell us what those numbers mean. So on the bottom, the last thing that's here is kind of talking about, again, what do those numbers mean? If you get something that asks you to interpret the p-value, they're not asking you to decide if you're going to reject or fail to reject. They want you to tell them what 0.0119 means. So what does that p-value, kind of going back to our pictures up here, what does that shaded region in our normal distribution, what does it represent? And so the kind of common sentence stem that I have is here, assuming the proportion of, this is where you fill in the null. Students who eat breakfast is 0.8, because the null is p is equal to 0.8. There is a 0.0119, that's my p-value, probability of obtaining a sample proportion at least as extreme as 0.6833. So basically that just means anything greater or anything less than, anything in a more extreme direction than this particular sample proportion in a sample size of 60 students at Jordan School due to random chance. So all you have to plug in is 4 things. What is your null? What is your p-value? What is your p-hat? And what is your sample size? And this question will always answer that. How do you interpret the p-value? So that kind of wraps up 6.2. Sorry that the audio didn't work the first time, but this should hopefully cover everything.